Now that we've discussed probability distributions and sampling distributions, we can kind of get at one of the key assumptions that we're going to be invoking when we use regression analysis, which is the central limit theorem. Critically different from the law of large numbers, and you'll see why that's the case. Most specifically, we are invoking the central limit theorem because we have a random variable from some sort that's produced from some sort of random sampling with a large sample of n, and we're characterizing the sampling distribution of that sample mean or something from that sample, a test statistic, and the assumption is that it's approximately normal, where the sample mean is going to equal the parameter or population mean, which is just some mu. And we can also characterize the spread, which again is going to be sigma over n squared. Or sorry, excuse me, the root, square root of n. The variance element here is going to be the standard error. Now, this is a little bit confusing because this is the standard deviation of the sampling distribution of a sample mean. So note that this formula includes the population standard deviation because we are talking about a population parameter. You really need to pay attention here because you're going to get these mixed up if you're not careful, right? The the standard deviation of the sample is going to have the square root of n minus 1 or something else in that denominator. Now, importantly, as n goes to infinity, this standard error is going to get smaller and smaller and smaller. This means that we're producing an unbiased distribution of the sample mean. We're going to talk about why this is important later, but trust me, it's incredibly important that the normal distribution is invoked when we're talking about things like how our error terms are distributed. We're going to make an assumption that our errors are centered around 0 and normally distributed. And when we make that assumption, we are invoking the central limit theorem. Now, normally when we invoke the central limit theorem, the kind of general rule is that n should equal 30, but there's really not a steadfast rule, right? So we want to increase our n toward infinity because that's going to reduce our standard errors. Now, for right now, this is going to work for everything, right? We can imagine for any type of sample mean that we want to talk about, we can invoke the central limit theorem in the sense that if we took repeated samples from our population and got a bunch of different sample means, the distribution of the sample means would converge to a normal distribution. Now, I kind of want to prove this to you, and so let's do our own little experiment in R. Now, all I'm doing here is generating a, quote, abnormal distribution to make my point. So you can see in the next slide that each draw or each sample that we have is not normally distributed. That's not what we're talking about. The important thing is what is the distribution going to look like after we have 100 or 1,000 samples and we look at the means from all of those. So you can see that, in fact, our distribution is centered around 0, but it is not normally distributed. In fact, it might be bimodal, if anything. So all I've done here is create a random sample, right? Now, I'm going to keep doing this 1,000 times. There's nothing special here about what I'm doing. I'm actually taking very small samples every time. There's only going to be 20 observations in each sample, but I'll have 1,000 observations. Now, what we can see is that once we increase the number of observations, or sorry, not the number of observations, the number of trials or samples, we can sort of see how this starts to smooth out. So by the time we get to 100,000 people, or sorry, 100,000 samples, regardless of how many people are in each of those samples, the sampling distribution of the mean tends toward a normal distribution. Now, I know I jumped through a bunch of code and I don't really want to harp on it. If you're interested in how I created these simulations as well as the graphs, please take the time and go back and look at the slides, but I don't think it's useful to use the lecture time to go over them. Please ask any questions though during office hours or labs if you have any problems understanding the material. Given that we now know kind of how the central limit theorem works and potentially when to invoke it, we need to understand the more nuanced elements of how it's going to apply toward describing the spread of something that we're interested in, right? Like how our errors are distributed. And it's very nice because it tells us not only the mean of that sample and how it should be associated to a population mean, but it also tells us something about the spread. And remember, we talked about the standard error, which is the standard deviation of the sampling distribution of y. We're denoting that as sigma sub y bar. And it can get confusing because I may refer to it as the standard deviation of the sampling distribution to try to be clear, or I may talk about a standard error. And this is especially important because later on when we're talking about regression analysis and we have coefficient estimates from our regression, we're going to have some bounds of uncertainty around that. And we're also going to call that a standard error, which is totally appropriate because those coefficient estimates are point estimates, and it is describing the sampling distribution of that random variable. So under certain circumstances that we'll talk about, we can assume that the sampling distribution of whatever point estimate we're interested in this case, y bar, is going to have the same mean as well as spread as a normal distribution.